Yes, correct. So apologies if you really wanted to get to the toric code today like I did. We won't see it today, unfortunately. So as I've written up here, we are going to get to some topological quantum error correcting codes in the next couple of weeks. But first we need a little bit of the machinery around general quantum error correction. And I'll just say that a lot of today has been taken from this textbook, which you may have already heard about. It is a very good one. A lot of the results and definitions that I'll be using today are written in density matrix, density operator form in the textbook, and I've tried my best to transcribe it into more like state vector form for the talk today. So there may be some transcription errors there, so bear with me if there are, if you see any. All right, so I'm going to start off just recalling a couple of definitions from 2 weeks ago with the classical linear codes that we saw from James's talk. So I'm going to write those up, as well as the sort of quantum analog. So to begin with, just recall the linear code. So linear code C of length n and rank k is k-dimensional subspace of F2n. Now the quantum version is the following. So quantum error correcting code is a subspace C of the state space, which is a Hilbert space. So the state space of a quantum system. So it's pretty easy to see the comparison there between these two different definitions. They're pretty similar, subspace, but the difference is sort of what the subspace is of. So F2n in the case of the linear code, the classical linear code, and the state space of a quantum system for the quantum error correcting code. I'm also going to write down just really quickly summary of the definition of a code generator for the linear code. So we had the notion of the code generator matrix. So the code generator matrix for the classical linear code Cs, and by K matrix G, that encodes these unencoded code words into the code words in that linear code there. So the quantum error correcting code equivalent is just a quantum circuit. So I'm not going to write that down as a definition, but we have a notion of an encoding circuit that we'll see some examples of later on. So again, we have that similarity between the two, the classical and the quantum versions. But the thing is, with quantum error correcting codes, we have a wider variety of errors that we have to correct for. Yeah. Yes, sorry. So yes, we have a wider variety of errors that we have to correct for in the quantum error correcting case. Which means we need like we want to have a fairly broad idea of a general theory of what those errors are, so we can have a general theory of correcting those errors. So that's sort of what we need to go to next, and to do that we need the following definition. All right, so we have this definition. A quantum operation is a map from the input space to the output space, such that for all vectors in the input space, we have this representation of the map. We have this operator sum representation, and those operators, we call these just the operator elements of the map E, satisfy this condition here. So this is going to be we'll see this as quite a versatile definition. It's going to actually allow us to encode like the error that happens in our system, as well as also the recovery of that error. So it's going to be quite useful to understand this. We'll also just squeeze this down the bottom here. So quantum operation is trace preserving when this is equality. Now, the notion of trace, sort of in this sense, it kind of encodes measurement in some way. We'll talk a little bit more about that later on, possibly more next week as well. Is everyone clear on that so far? Yeah. Well, both. But in this case, I kind of just want to call it trace preserving because we're not going to really look at traces today. So, yeah. But we do use the notion of trace preserving in a definition later on. So I just wanted to show you now. All right.
It's equivalent to trace of the left-hand side applied to any vector is equal to 1.
All right. So our first theorem, I won't actually prove today. It is in the notes if you want to have a look. So it discusses the uniqueness of these quantum operations. We're going to see that there's a criteria for two quantum operations to be the same. So suppose we have these two sets of operation elements that define these two different quantum operations. So, well, the way I've written it in the notes, it has like E goes up to M and the F go up to N, so 1 to M. And we can basically take those two to be the same size. So, you know, if they weren't the same size, we can just add some like zero operators to that set to make them the same size. So we're just going to just assume, without loss of generality, that they are the same size. So then these two are the same if and only if only if there exists complex numbers U, I, J. That form a unitary matrix. So like I said, I won't prove that right now in the seminar, but we do use it later on, so I did want you to have that result on the board. All right, so we kind of jump through a little bit through the notes if you're following along with the notes. Coming over to a couple of propositions. All right, so pretty simply, it just means that if you have two quantum operations that are compatible in terms of the right domains, you can take decomposition, that's also a quantum operation. Pretty simple proof, you can just write it out in that operator sum form and you see what operators you get, operation elements you get for this quantum operation. We also have the following, rather informally, measurement is also a quantum operation. Yeah, I won't talk too much about that at the moment because I want to get on to probably the key part or the key parts of this talk. So yeah, pretty much now we're at a point where we can make our sort of minimal assumptions about error correction. Okay, so in the next definition, I'm going to use the term error channel, and basically by error channel, I just mean a quantum operation that's like a model for a certain type of error. And then the word channel, I guess, sort of arises if we have sort of our quantum system and, you know, evolves in time, you can sort of view that as going through a channel that's noisy, something like that, okay? Yeah, but specifically one that it represents or affects an error model. And we'll see a couple, well, we'll probably see one error model today and I'll talk about a couple others. Yeah.
Worth remarking that the idea there is that E represents the sort of effect on our actual system of some unitary operation of bigger space. This is what's left over.
Yeah. Yeah. So did everyone catch what Dan said? Yeah. Okay. All right. So looking at this, so an error correction procedure is a trace preserving operation, quantum operation R, such that we have this, and this is a proportional. So basically, this proportionality here arises from the fact that we haven't made any assumptions about our error channel, our quantum operation that models the error. We haven't made an assumption about that not measuring the system. So if it measures the system, then we don't have equality here, whereas if it doesn't measure the system, we do have equality here. Because R is trace preserving, we're saying that our correction operation doesn't measure the system. Okay? Yeah?
If E is not trace preserving, can you still have proportionality?
Yes. So, yeah, that's sort of what we're saying. That, yeah. And we'll see very shortly that we have a theorem that gives us conditions for when we can actually correct error. So basically, there are restraints on the operation elements of this quantum operation E for which we can correct. Yeah, yeah.
In other words, R may not always exist.
Yes.
For a given E.
Yeah, correct. So that's the comment I should be making now. Yeah, we say that error correction can exist or can proceed if this exists. Yeah, yeah. Yeah. Okay. All right, so let C be a quantum code. I just realized I've made a bit of a mistake with the earlier definition about what a quantum code is. I was meant to add on that we often view the code alongside a projector for that code. It projects onto that subspace. So that's sort of what we're going to use in this theorem here. So we have the code, which is the subspace, along with the projector, which is called PC. I'm probably going to just drop the subscript pretty soon. We suppose we have this error channel. So for this error channel, there exists an error correcting procedure R that satisfies that equation over there, if and only if the following holds. So it holds for all I and j of these elements here, where this matrix is Hermitian. So we're going to do basically one direction of this proof. So we're going to go from this, supposing this holds, to finding an error correcting procedure. And partly why I wanted to do it this way is because it's fairly instructive of how we actually go about correcting errors, which we'll see in an example a little bit later on. But yeah, so this gives us a pretty nice little sort of test to see if our set of errors can be corrected. So if this doesn't hold, then we can't correct for those errors. All right, so the proof. So I'm going to drop the subscript on the projector here. All right, so supposing this holds, now we can diagonalize this matrix alpha. So diagonalize it to some matrix D. That U is unitary. And we're going to define this new set of elements like so, using this unitary matrix. So we know from our first theorem, 1.1, that this also describes the quantum operation E. Okay, and it's going to be a little bit useful because it allows us to diagonalize this sort of stuff here. So I might go to this board up here. All right, so let's consider this. So just going straight from that, this here. This is where we're using the assumption. And we're using the diagonalization. Now, so we're going to have a look at these operators. So consider the operators FKP, so sort of this guy. We're going to take the polar decomposition of this operator. So I haven't written up anything about that yet, but it is in the notes. There's a theorem that discusses the polar decomposition. Basically, we can write this operator like so. For some unitary UK. And we see that this equals square root of dkk UKP. Okay. All right, so these operators are, these projectors, sorry, are orthogonal. Sorry, we're going to define. I skipped ahead just then. We define the following projectors. And we can see that these are orthogonal. Yes. Yeah. So polar decomposition. This is a positive operator in unitary. Have we got the wrong way around? Well. Yeah. 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 And so we know like the J is the unique solution to this with j, for unitary u is j defined like that. And so, yeah, our FKP is A, and this is A dagger A. Yeah.
The second equality, you use this calculation above.
Yes. Yeah.
So then the second thing over there is actually KU. K is square root A dagger. And you use those equations to calculate.
Yeah. Yeah.
And you don't care about the D's possibly being negative because phases are all put into decay?
I guess I haven't thought about that. Yeah.
Because DKK can be negative, but it's a real, but it can be negative.
Yeah.
And you want the square root to be something positive.
Yeah. Yeah.
At least on the left hand side, it's something positive. And on the
Mm.
right hand side, it's potentially something negative. Okay, so maybe it's just that the U is different.
Okay.
I think you just need some UK, whether you call it UK or
Yeah. I was under the impression we need them to be the same unitary.
Let's just proceed and then see if it's an issue.
Yeah. Okay.
Discuss it.
All right. So we're showing that they're orthogonal for L not equal to K. And just sort of following the notes, as you can see, we have this taking its conjugates the same for the projector, and you can just expand that out. So we've just used, we set it on the board, this up here. And basically when K is not equal to L, that is 0 because it's a diagonal matrix.
Do you somehow this earlier statement that this collection of FKs is also a determinant quantum operation?
As in to solve what we were talking about before, is that what you're saying? Or
All of that is pretty fine. I'm just wondering to answer this question.
yeah. Okay. Yeah.
But once you have this last point there, so why was D okay with 0 but
Because it's a diagonal matrix. Yeah.
okay.
Yeah. All right, so this next bit I think is quite informative, especially as we get to a specific example later on, because we're actually defining the operation elements for our correction procedure using some of what we've done here. So we define R by the elements So for any element of the code space, we have this. So that's just expanding that out. And that's just because psi is already in the code space, so they're equal, psi and the projector applied to psi. So next we're going to expand out this term here, the pk dagger. And so what we have in the middle here is, oh, it's gone now.
Can you expand this first line? Curly E is defined as E.
Yeah, but it's also the same as using the F elements. So we use the first theorem that we saw to show that when we write down the elements F that are a sum, like it's a unitary equivalent to the, yeah, it's the exact same, yeah. So like we can write like that, yeah. All right, so we know that this is 0 unless k equals L. So we get this, which obviously simplifies the sum down just over k. And if I just do that, we see that's proportional to that vector, which is precisely our definition of quantum error correcting procedure R. So the only thing that remains to show in this first half of the proof is the sum of these pk's, the sum of these operation elements equals I. So we need to have the trace preserving. But pretty much we can just append, if it isn't the case already, we can just add projectors to that set to make it so. So I'll just sort of write that in this box.
Is there potentially an issue with the sum that you have there should be non-zero? Which of course it is if all the square roots are positive numbers, but that requires sort of the change of the rules that I was mentioning earlier on.
Right.
So you definitely want this to be non-zero, right?
Yeah.
Because
Yeah.
otherwise it's zero.
Yeah.
It's corrected, error is corrected. Okay, good.
Yeah, so to show, the last thing we need to show with being trace preserving. So equals I when we've added a projector to that set. All right. Yeah. So pretty much, we'll get there pretty shortly. In the example for the bit flip channel, the bit flip code, we're going to write down the PK up there. And from there, we can go to these operation elements there. Yeah. All right, so I won't go through the second half of this proof. It is in the notes there. We'll write down another important theorem that we won't prove and then get on to the example stuff. So. This, yes. All right, so this theorem says that if we have a quantum error correcting code and we have this error correcting procedure that corrects this set of errors, then it also corrects this other quantum operation or error channel that is related to this set of errors by this matrix here. And this is a really important theorem because it allows us to correct for like a continuum of errors via a discrete set of errors. So it's going to be really important later on because the errors in the quantum sense, yeah, it's a continuum. So just as a sort of sketch for this proof, it's pretty similar to the theorem we've done here, or the part of the theorem we've done here, where maybe we should write some of this down. So we assume that we have this case where it's diagonal again, then we can just do the same trick that we did last time if it's not. And then you define the operation elements of quantum error correcting procedure R to be pretty much the exact same. So as elements where those are defined similarly, then so that's the same as before. So we pretty much get the case. I think I made a mistake in here. Oh, no, I have it. Never mind. So when we consider the case for the errors F, so that's just really briefly going through some of the steps. Basically, because we have this condition, or this case, when you go through there, we still find it's proportional. Okay, so that's a very brief proof of that, or sketch of the proof of that. All right, so let's go on to some examples to see how this works in practice. All right, so let us denote the bit flip channel as follows. So with probability P, it doesn't do anything to the state. With probability 1 minus P, it acts as X, or bit flip on the state there. So we can draw the encoding circuit as follows. All right, so we encode this state. Yeah, so we're going to have the actual error channel for this is going to be 3 versions, like the composition of 3 independent models. Yeah. All right, so this is the quantum equivalent of that code generating matrix that we wrote down, or the definition for earlier. So like this is the quantum equivalent of the classical code generating matrix. And you can work through the details to show that that is actually encoded as that through this circuit. These are C0 gates there. Question?
Just to clarify,
Yeah.
that second line, there's no interaction with the first zero.
on this one here?
Yeah.
No. Yeah. And so the error channel for this code so I've just written that as a bit flip channel on the third qubit, second qubit, and first qubit, and these are all independent. So if we sort of look at what that looks like for some psi prime, so psi prime like this here. I will write. So for each of these channels, we're going to have the same probability p, just to make it a little bit simpler to write it down. So. So you're going to go through the details of if you wanted to expand it out one by one, but I'm just going to jump straight to the answer here. So this notation means that x applied to the third qubit and implicitly implies that identity applied to the other two qubits. So probability that nothing happens, probability that each of those individually, a single qubit error happens, probability of 2 qubit errors, and probability of a 3 qubit error. And if you wanted, you could go through with each of these elements and plug it into that theorem we had before that gave you some conditions for testing which sets of errors are correctable. And you will find that it's only the sort of no errors and single qubit errors that we can correct, given that the projector for the code. So I haven't even really said what the code is. I'll write that over here. So the code is spanned by, or the subspace spanned by those vectors. And the projector is this. But now, if you remember back to that theorem that we looked at before, we had those projectors pk. So maybe I'll write them here as well. We're going to have p0 is the same as p. p1 is going to be this. Sorry?
So P sub k, so k is the index of the operators in curly.
Yeah. So
Here, when you compose them like that, you multiply the sum as well. So there's actually 8 things in curly.
I guess sort of what I'm saying is we can correct only for the set of 4 things. So it's kind of like this is sort of what you get when you have the 3 independent models, error channels, but we can only really correct for, I don't know, E prime has these error components, I guess. Maybe I'm not saying that clearly enough. So if we went from here, we have, so if we wrote down this as, the set of operating elements that are all the ones there, and we looked at which subset of that we can correct for via the machinery we had before, the theorem, then we get this.
So you essentially think about epsilon prime as being some finite location of the Taylor series or something like that.
I guess so. Yeah. So pretty much, so we don't run too much longer. So like we did before, sorry. Yeah, so that's what I'll write down now. Yeah. And then we'll see how that works for a specific error. So So if we use, if we take this as we have up there, we apply it to, I'll call it a prime error channel, and say we get out this case. Yeah. Yeah, I mean, I guess I think more about the syndrome measurement in terms of the stabilizers, which we haven't talked about here. But I guess so. All right, so we have this. If we apply our error correcting procedure to it, then obviously we have each one applied. I'm just going to, I'll call that psi double prime. Now all of these are going to be 0, except for the second x2, p2. So 0. So this is the, and that's the encoded word, yeah. We've put it through the error channel. It's picked up an error on the second qubit, and now we're correcting it. And I'm just sort of showing you that that's sort of what. So it's come out with a probability p, or that it's flipped that second qubit. So it could have flipped anyone. I'm just saying that this is the error that we got out, which we sort of don't know. But if we had done this regardless, so like even if this was just arbitrary error, this will always come back with the right state.
The point of the presentation in terms of state vectors is becoming confusing. So, actually, this prime or psi has p's in it, and you kind of sampled from that.
Yeah.
And that's this thing.
Yeah. Yeah.
So you can go through again. First two things are 0 because p is projecting onto the zeta. P1 is looking for what?
First case. Yeah. So yeah, I guess the point is, yeah, if we hadn't known that this was the case, then so long as it was only one error, this will always return this, regardless of what this turned out to be. Yeah. So I guess we'll pretty much stop there. There is also the phase flip channel, which we may go through next week, as well as called the depolarizing channel, which is basically the composition of those two channels, the bit flip and the phase flip. And basically with the last theorem that we went through, theorem 1.7 in the notes, it shows that if we can correct for the x and we can correct for z errors, which is the phase flip error, then we can correct for any single qubit error, any arbitrary single qubit error, which is an important result going forward for the toric code and things like that. All right, are there any questions?